everyone, welcome to my video series on statistical significance testing. So in this video we are going to talk about the t-test. Now in the previous video we also talked about the z-test, which is very closely related t-test as well. Now within t-test we are going to sort of cover all the possible variations, which is one sample t-test, unpaired, two sample t-test, and paired t-test. Okay, so without further ado, let's dive in. So, first of all, let's understand where do we apply the t-test. We apply t-test for the cases where we actually want to apply z-test, but we cannot. So basically, there are situations where we want to apply the z-test, but for some reason, we cannot. So what are those reasons? Number one is population standard deviation is not given. For example, if you are trying to compare heights of Indian men and you don't really know what is the standard deviation of the Indian men heights overall India, then you cannot really apply the z-test. Now, as you can understand quite easily, that this is not really feasible in most cases. So in most cases, the population STD is not really given. Then if your sample size is less than 30, then z-test is not a good fit. So there are three types of t-test. They are one sample t-test, unpaired or independent, two sample t-test, both are the same thing. Then there is paired t-test, and it is also basically two sample. So paired t-test is also two sample t-test. Okay. Now, this is how the t-distribution looks like. Now, if you don't know about t-distribution, you can follow my video on t-distributions in my probability distribution series, but I'm going to leave a link in the description as well. So just to clarify, as I said, that when sample size is less than 30, we have to use the t-test. Suppose sample size is only 6, so there are 6 samples in our data set. In that case, degree of freedom will be 5. 6 minus 1 equal to 5. That means higher degree of freedom means that you have more samples to compare, right? Okay, so as you can see, when we have only 1 degree of freedom, see the curve right here, the purple curve, the tail can be quite fat, right? As we increase the number of samples and the number of degree of freedom, the curve gradually becomes less fat-tailed, the tail starts becoming flattened, and after 30 degree of freedom, the t-distribution sort of looks like the normal distribution, right? That is how the t-distribution behaves. Let's now understand how to actually read the t-table. So there is something called the t-table which we're going to use to calculate the probability, the p-value, the critical region, those kind of things. So we need to sort of have an understanding about what it looks like and what it actually represents. So suppose this is our t-distribution curve and n equal to 6, that means there are 6 samples. That means the degree of freedom is going to be 5. You can see in this table that these are the degrees of freedom. These are the degrees of freedom and these are the p-values. These are the probability values where t greater than t. I will talk about this in a second. And these values right here, those are t-scores. Okay, so let me clarify what I mean by this here. So you can see that for degrees of freedom 5, which represents n equal to 6, and for a p-value of 0.05, we have a t-score of 2.015. So what does that mean? Graphically, it is basically this. So in the x-axis, you have the t-scores, and in the y-axis, you have the density values. This is just like a normal probability density function. And you can see that this region right here, beyond 2.015, so where did 2.015 come from? It came from right here. So beyond 2.015, the area that we have, that area is going to be 0.05, right? That means probability of t greater than 2.015, that means this area is nothing but equal to 0.05. That means it has 5% probability. So this is how basically you read off from the table. I hope you understand this part. So if you now know how to read from the table, now we can solve some problems, some questions, and see the 3 variations of t-test with concrete examples. So here is the first example. Assume we have taken the weight of 10 Bangladeshi men in kilograms in kg who eats fast food regularly, and these are their weights basically. And the mean weight of Bangladeshi men overall is 75 kilos. Now, maybe you got it from the statistics office, right? Statistics Bureau office. So you can contact them and you can ask them what is the mean weight of Bangladeshi men this year. So they will give you some number. Now understand that the standard deviation is not given right here, right? I think that is clear to you. So the question is, are fast food eating men significantly fatter than typical Bangladeshi men? So understand that this is basically one-sided, right? Because they are talking about being fatter. That means extreme value to the right. So the side is given. So here what we are going to do is we are going to do a one sample t-test and it will be one-sided. So why one sample t-test? Because we have only one data set. We have only one data set right here. We are going to compare that with some mean number, with some mean value, which is a global value, right? So this value right here is a population level value, right? But the standard deviation is not given. So it will be one sample t-test and one-sided because it has talked about the right extreme. So from these 10 values, we can get the mean sample weight as 81 kilos and standard deviation as 2.58. So these are the null hypothesis, nu equal to 75. That means the mean is actually not different from 75 kilos. And H1 means nu greater than 75. That means the people are significantly fatter. So that is the null hypothesis and alternate null hypothesis. Alternate hypothesis basically. Okay. So we can get degrees of freedom equal to 9 because there are 10 samples, 10 minus 1 equal to 9. And this is the formula for the T score. Now it is extremely similar to the Z score formula that we talked about in the previous video. I will leave a link of that video in the description as well. So you can just plug in these numbers that you got right here and you will get the T score. Now one thing you may ask me, why do we divide by root n? So the answer is very simple. Here we are trying to divide by the variance, not the variance, I'm sorry, the standard deviation. Now the standard deviation is with respect to the mean value. So you see that in the numerator we have the mean values. The standard deviation is basically of the mean value of the x prime, right? And obviously, if we have more samples, we are going to have a lower variation in the mean measurement. That means lower variance. And that means we have to divide by n for lower variance. Now, we are not talking about variance here. We are talking about standard deviation. So standard deviation is nothing but square root of variance. So we are going to get the square root of n. That is basically the hand-wavy intuitive explanation of why the root n is there. But the main thing that you need to know is that this is not a single sample, rather this is the mean of the samples. So when we talk about the deviation of the mean of the samples, there we need to divide by this number because the mean will be more and more accurate once we have more and more samples. Okay, now that we know the t score, how can we actually get the p-value, or whether we can reject the null hypothesis or not? How can we decide that? So you know that if this t score that we just obtained is basically false right here, then we can actually reject the null hypothesis, right? So okay, where does this 0.05 belong? This 0.05 actually belongs here. You know that in this question, degrees of freedom was 9. So at this point, 1.833 was the critical value of t. So this is the critical t score. Now the question is our 7.35 t score bigger than this? Yes, that means it is to the right side. That means it definitely falls in the critical region. And so obviously we can see that the p-value will be less than 0.05. We can reject the null hypothesis and we can conclude that the fast food does make men significantly fatter. So this is just one part. Now let's look at another example. So here we have two data sets right here. You can see this is one data set and this is one data set. So assume that we have taken the height of 15 BD men and 15 BD women, BD for Bangladesh, and these are those heights. We want to know if the BD men are significantly taller than the BD women. This is what we want to know. So these are men heights, these are women heights. These are men heights and these are women heights. Now, this is a very ideal example of unpaired or independent two sample t-test, and it is one-sided. Why? Let me explain first. First of all, this is just one group. This is just one group of height and this is just another group of height. So there is no dependence between these samples. So 168 is not linked to 158 or 160. They are not linked with each other. That is why they are unpaired or independent. It is two sample because there are two datasets involved and we want to compare them. And this is one-sided because we are trying to see significantly taller. That means right extreme. We have talked about right extreme. That is why. Okay. Now, this is going to be our null hypothesis. That means new one, the mean of the men BD height is going to be roughly equal to the mean of the women BD height. But in order to reject that, we will have to say that new one is actually greater than new two. That means men are significantly taller than the BD women. So first of all, we can simply take the mean. We can get the mean from here for men x1 bar and x2 bar for women. Then you can also calculate the variance of men and women heights. And we can get the degrees of freedom like this. So this is very, very crucial. So understand that there are two versions of the unpaired two sample t-test. One is the student's t-test and the other one is the Welsh t-test. Now, Welsh t-test is a very recent development, but more popularly in the history, people always used the student's t-test. So in the student's t-test, there is an assumption that we have to actually merge all of these values together, and based on the merge of all of these points together, we can actually get the combined variance, combined degrees of freedom, and so on and so forth. That is why you can see that this is the degrees of freedom n1 minus 1 of the men, and this one is for the women, but we're adding them up to make them 28. So we are acting as if all of these come from the same place, right? Okay. Now, as I said before, we have this assumption of pooled variance. So pooled variance means we are going to put everything together and then get the variance. So how can we do that? So this is the formula of the pooled variance. So SP square is actually nothing but a weighted, right? Weighted version. So you are weighing S1 square by N1 minus 1, weighing S2 square by N2 minus 1, and then normalizing. So this is going to be the pooled variance, right? SP square. But the whole game is not over yet. Let me proceed first. So we can get 5.04 from here. Now, obviously, this is SP square, this is variance. So standard deviation is nothing but the square root of variance. That is okay. Now, if we want to get t, the t score, this was the formula for the t score, right? You know from before the previous slide, from the previous example. Now there is no new right here. There is no mean population level mean right here. There is x1 bar and x2 bar. So you can replace by x1 bar and x2 bar. Now the thing is, what is the variance that is here? The variance is of what is there in the numerator. That is what I have written here, variance of x1 bar minus x2 bar square root, because ultimately we will need to put standard deviation right here. Now, if you know your math, you know that the variance of two variables is nothing but the summation of their variance, right? Although this is minus, don't be fooled by that, but there are two variables, so you have to add those variances, because we are actually assuming that x1 bar and x2 bar, those are actually independent, right? Those are independent because this is unpaired, right? So obviously that assumption is correct. Now, what is the variance of x1 bar? It is nothing but sp square by n1. Now you may ask, why do we divide by n1? Right? Why do we divide by n1? It's very simple, because this variance is actually the variance of not single variable, but it is the variance of the mean. And we know that the mean variance actually becomes smaller and smaller as we take more and more samples. And so divided by n1 will be there for x1 and n2 will be there for x2, and both have sp square because we are making this assumption of pooled variance. So if we just take the sp out, this will be basically our t-score formula. And if we plug in the values here, you are going to get something like 13.88, right? Okay, fine. We know the t-score right now. So we can do the exact same thing we want to get here. This is one-sided test. We have 28 degrees of freedom, like I said in the previous slide, and we want to get this significance level. So we need to get 1.701. 13.88 is bigger than 1.701. Now hypothesis rejected. So BD men are taller than BD women. I think it's very clear now. So this is the second example. Now for the third example. Assume that we have taken the height measurement of 20 Bangladeshi boys before and after drinking a supplement drink regularly for a year. So basically there are 20 Bangladeshi boys, maybe they read in the same school. So they were given some kind of supplement drink for 1 year. Their height was measured in the previous year and then also in the next year after they consumed the drink. Now, these are those heights. You can see that for boy number one, the height was 150. After drinking, the height was 152. The boy number two, the height was 152 centimeter. And after drinking, it was 154, and so on and so forth. These heights are there. Now, the question is there any difference in height after taking this supplement drink? That is the question. Now, this is a classic example of a paired two-sample t-test, and also it is two-sided. Why? Why it is paired? It is paired because 150 and 152 are linked. It is for the same boy. 152 and 154 are linked. It is for the same boy. So all of these measurements are actually for the same boy with two time steps, 1 year before and 1 year after drinking the supplement drink. That is why they are paired. Why it is too simple? Because there are two data sets involved. That is why it is too simple. Finally, why it is two-sided? It is because we are only trying to measure if there is any difference in height. Now that height difference can be smaller. That means it can be the left extreme or it can be significantly larger. It can be the right extreme as well. But we don't know which one it is. We just care about the difference, significant difference. That is, we just care about the significant difference. That's all. Okay. So the first thing we have to do is we have to take the difference after minus before. So 152 minus 150, 154 minus 152, and so on and so forth. If we do that, we are going to get all these differences, right? And the mean of these differences is 1.8. The standard deviation is going to be 0.41. You can do the math. It's very easy. Now, this is going to be your TS score. Now, the question is, why don't we have some kind of subtraction here, like x prime minus nu or something like that? Because we have already done the subtraction right here, right? So we don't need to do it again. So d bar, and below there will be the standard deviation thing, as I discussed in the previous two examples as well. So if we do the math, we are going to get 19.63. So the degrees of freedom will be 19. Now this is very, very important. Some people may think that we have to do 20 minus 1 plus 20 minus 1, just like in the previous example, but that is not true because there are basically 20 boys right here. So it's not like there are 20 boys in this data set and 20 other boys in this data set, but these are all 20 boys. So total number of people are 20 basically. That is why we just do 20 minus 1 equal to 19 degrees of freedom. Okay, fine. Now we do this exact same thing, but here there is a trick because it is a two sample t-test, as I said before. That means the critical value can be either at the bottom or at the top, and we want to get 0.05 significance level, that means 5%. So 2.5% at the right extreme and 2.5% at the left extreme will be here. Now, at degrees of freedom equal to 19 and at 0.025 significance level, you can see that this is 2.5%. That is why we are looking at 0.025. The value here is 2.093. You can see that the t-distribution curve is symmetric with respect to 0, but that means it looks the same to the left and to the right. So we can actually put 2.093 here and minus 2.093 right here. We don't need to look up this value again from the table, right? Now we can see that we have a value of 19.63. 19.63 falls where? It falls somewhere right here, which is actually to the rightmost side. And so it falls in the critical region, again, rejection of null hypothesis. And so the supplement does bring significant difference in height. And you can even say that it brings significantly positive difference in height, basically. So that is all about the t-test. If you like the video, feel free to subscribe and share. And also, if this video was helpful, you can donate to our channel via the link in the description. Thank you very much.